Hi everyone. In previous lessons, we have learned the fundamentals of programming in Go. In this installment of Programming for Lovers, we are ready to start applying these fundamentals. In particular, we will implement a trivial algorithm for computing a greatest common divisor of two integers, and then compare that approach against Euclid's algorithm from 300 BC. How much faster could such an old algorithm be? I think you're going to be surprised. So why don't you join me and find out? As always, if you enjoy what you see, please like, subscribe, and join our course at programmingforlovers.com. Let's code. To get set up, you'll see that I created a folder called GCD under Go SRC in our File Explorer on the left side of VS Code. And I've also created a main.go file within that GCD directory. And you can see I've started to add a little bit of code to that. So go ahead and get your package main declaration at the top, add import fmt, and have a func main that just has a print statement. I'm going to explain the other things that are present in the code as well. One being our min2 function. So we've already written that function before when we talked about conditionals. So I've simply copied that function over. You might want to copy it over yourself or rewrite it if you like. And I also have some pseudocode that we're going to find useful in this lesson. So we're going to be implementing our two GCD algorithms, what we call a trivial approach that simply ranges through all the possible divisors of A and B and sees the largest one that it can find that is a divisor of both A and B. And then we have Euclid's approach, which is based off of this mathematical theorem that if A is greater than B, then the GCD of A and B is equal to the GCD of A minus B and B. Simply iterating that idea over and over again to subtract the smaller number from the larger number until the two numbers are equal. And then once that's the case, we know that the remaining number is the greatest common divisor of the two numbers. That's a not immediately obvious fact that we discussed in the main text, but it allows us to have a second Euclid GCD algorithm that's based off of that idea. So successively, while the two numbers are not equal, subtract the smaller number from the larger number until such a time as they are equal, and then you know you have the GCD. So those are our two algorithms that we want to implement in this code along, and I'm going to get started with implementing trivial GCD. So we'll implement both though, and then we're going to discuss the runtime of these and see whether or not the Euclid approach truly is better. So we'll look at trivial GCD first. And if we look through the pseudocode, we have a min2 subroutine that's already been written. We know how to set a variable d equal to 1, so those two lines are fine. What we have just seen with working with loops is we know how to range some integer p between 1 and m. And all that really we haven't quite talked about is this statement here, if p is the divisor of both a and b. So if that's the case, we want to set d equal to the value of p, and then we'll eventually return d after we try all possible p. But this one line, if p is a divisor of both a and b, is what we're going to find where we're going to need to talk about something that we haven't quite seen thus far. So in the meantime, I'm going to have my function comment. So trivial GCD takes as input two integers a and b and returns their greatest common divisor, GCD, by applying a trivial algorithm attempting each possible divisor of a and b up to their minimum. All right, so our function signature, our first line of our function is going to be func trivial GCD a comma b int, and it's going to return an integer as well. And what we will do is simply start converting the pseudocode. This is the benefit of having thinking about algorithms on the level of pseudocode. Regardless of what language we're using, we just need to convert that pseudocode into the syntax of that language. So we're going to set d equal to 1, and eventually that's going to be what we return. So d is going to store the largest divisor that we have found thus far. I'm going to set m is equal to the minimum of a and b, and then we're going to range over all possible integers p between 1 and m. So we're going to have we know how to do that. We're going to have a for loop. And remember that a for loop has those 3 components. So we have the initialization step. So we're going to set p equal to 1. We're going to have the condition, which is what we test every time through the loop. So p colon equal to 1 is the first thing that will happen. Then every time through the loop, we need to make sure that we haven't exceeded m, since we don't need to go by the minimum of the 2 numbers in order to consider a greatest common divisor. And then every time through the loop, we have our post condition of p++, where we increase p by 1. So what remains here then is to handle this if p is a divisor of both a and b. And I would like to present one way of doing this. So we know from previous work how it is that we find whether or not p is the divisor of one of those integers. So p is a divisor of a if, when we take the remainder, when we divide a by p, which in Go is represented by a% p, that's equal to 0. The problem is we need to check both a and b. And one way of handling that would be to have 2 if statements, and we're going to nest the if statements. So one if statement is going to be inside of another one. In particular, if p is a divisor of a, so if a% p is equal to 0, if that's true, let's now check if p is a divisor of b. So inside of this if block, we're going to say if b% p is equal to 0. And if we are here, in that if block within an if block, we know that p is a divisor of both, which is what we want. In that circumstance, we said, what do? We update d to have the value of p. So d equal p. And after we range that for loop over all possible p, we're eventually going to return d. Now, one thing that we might do to make that algorithm a little bit better is we don't need to start at p equal to 1. We could start at equal to 2. It's not going to make a great deal of difference whether or not we started at 1 or 2, so I'll just keep it at 1 for now. But we can verify this works. So I could come into func main, and we could go into func main and fmt.println. Let's print the trivial GCD of 2 small integers where we know what their GCD is. You can pick your 2 favorite ones. I'm going to pick 63 and 42. So I know that their GCD is equal to 21. 21 is a divisor of both, and there's no larger divisor of both of those integers. So I can go down to the bottom of my VS Code window. I'm in my home directory, and I'm in Go within that already. So I'm going to cd into src GCD, and then I'm going to build, and then I'm going to run. And I see that 21 gets printed. So I would need to test this on a larger collection of inputs, but it appears that trivial GCD, at least on these inputs, is behaving as expected. We don't have any compiler issues. That's the critical thing when I'm coding. I typically will have as many compiler issues as anybody else. So we've got trivial GCD written, but there's a way of making it better. A lot of times you can't help having a nested if statement or nested for loops. I think that any time that you can avoid them, as long as you're not slowing your code down, it's just good practice to try and avoid them. And in this particular case, we can avoid having 2 separate if statements if we have code that mimics what it was that we were trying to do in the first place on the level of pseudocode, which is to say, is it the case that p is a divisor of both a and b? Maybe we can do that check in just a single line. And so we are going to be able to do that by replacing if a% p equal to 0 by expanding this out and having an and keyword, which in Go is represented by double ampersand. And then we're going to move the b% p equal to 0 after the and. So this statement you might think about it as being parenthesized in a certain way. Go is automatically going to parenthesize, you can think about it's going to evaluate each of these separate expressions on its own. But if you want to add these parentheses just for the sake of clarity on your own end, I think that that's fine too. So this first statement is going to check, is it the case that P is a divisor of A? The second statement is going to say, is P a divisor of B? And each of those is going to return true or false based off whether or not each of those arithmetic statements is true. And so we will only enter this if statement if P is a divisor of both integers. And if that is the case, we'll simply set D equal to P, and we only need one if block. If it's the case that either of these is false, then we're not going to enter the if block at all. So we will bypass the if block entirely, and we'll move on to the next potential value of P, unless it's the case that P exceeds M, in which case we're going to be finished and we're going to return D. So that and keyword is very helpful. And I wanted to take a moment to discuss the other very, very commonly used keyword for joining logical expressions or Boolean expressions, which is OR. And to show that, I thought that it made sense to just provide a truth table here. So and in Go is represented by the double ampersand, and OR is represented by the double pipe. And so you think about the values of two variables, X and Y. They could be Boolean expressions as well, but as long as they have the values true or false, then you can join these things together in the way that we joined A% P equal to 0 and B% P equal to 0. So each of those things could be true or false, and there's 4 possible outcomes for the 4 truth tables, truth values of the things that you plug into an and or an or. They could both be true. And in the case of and, that's the only time that X and Y is going to be true. In every other case, so when X is true and Y is false, or vice versa, or when they're both false, in all of these cases, you're going to see that X and Y is false. So the only way that X and Y can be true is if they're both true. X or Y is different. So X or Y is false only when they're both X and Y are false. In all other cases, X or Y evaluates to true, meaning that we just need one or both of X and Y to be equal to true. If X is true and Y is false, X or Y is still going to be true. And if X is false and Y is true, then X or Y is still going to be true as well. So we'll use and or quite a bit when we're programming, but I wanted to introduce them here. And one thing that you might think about is, all right, using those truth tables, what would happen if I were to replace that and with an or? The function will be incorrect, but you might think, what's going to happen here? What exactly is the function going to return? It's going to return something. It's not going to be the GCD, but what is it that it's going to return? So I'll leave that to you to think about. In the meantime, I'm going to replace that back with an and. And I'm going to say one more thing about this, which is, let me remove these parentheses, and I will point out one very common pitfall that I've seen with students when they program, because it's a very natural thing to do. And that is to do something like this. Going back to our notion that when we do arithmetic and now logical expressions in Go, we have to be very, very precise. We can't say, for example, 2x and assume that Go is going to know that that means 2 times x. In this particular case, this type of expression looks good to the human eye. It looks like we're saying if when you do A% P and when you do B% P, they both have to be equal to 0. But A% P is an integer. It's not a Boolean value. It's not going to give you a Boolean value. Whereas B% P equal to 0 is. It's going to be either true or false. And so Go needs that Boolean value. So that's why we need to tell it if A% P equal to 0. It's otherwise not going to be able to interpret that. So I'm going to save that for now. And that's really about all I want to say about trivial GCD. You, in a previous code along, had an opportunity, if you wanted to implement Euclid GCD So you might like to copy your implementation into this file. I'm going to show an implementation of Euclid's algorithm. One thing that I want to point out is, as an algorithm, it's shorter. And even if it relies on a mathematical fact that might not be intuitive or obvious, in terms of implementation, it's going to be very, very short. So let's do that. Remember that we're going to take two integers as input, of course, and while a is not equal to b, we're going to have two checks, which is if a is greater than b, we'll set a equal to a minus b. Otherwise, we set b equal to the value of b minus a. So a and b are going to keep getting updated until such time as this is false. And when that's false, a and b are equal, and I'm going to return a. I could also return b because they're equal. So let's implement that function. So I'll say Euclid GCD takes as input two integers a and b and returns their GCD following Euclid's algorithm. So I'll have func Euclid GCD a b int, and it's going to return an int. Remember, in Go, we do not have the keyword for. We simply use, or we do not have the keyword while. We simply use the word for whenever we want to represent a while. So we'll say for, and remember also that when we have a not equal to symbol, to represent that in Go, we're going to use exclamation mark equal to. So while a is not equal to b, that's how we read that out, we're going to have a check. Is it the case that a is greater than b? And if so, set a equal to the difference between them. Else, we know that b is greater than a. Why? Because it's not equal to a and it's not smaller than a. So if we make it here, we know that b is bigger, and we're going to set b equal to the value of b minus a. Once we make it down here, we can return a or b because they are equal. We know that they're equal because we've skipped past this while loop. This while loop is finished, so we know that they must be equal. All right, so that's a short algorithm to implement. Again, I'm just going to save and compile. And we can verify that it's working on the same inputs. So let's see if we get, when I call Euclid GCD, let's call it on 63 and 42 again, and I will save that. I will compile. Ooh, I got an unexpected comma. Line 12. I think I have too many inputs there. All right. I told you I made a lot of compiler errors, so I was right. And we see that Euclid GCD of 6342 is also 21, as if by magic. All right. So what we really critically care about, though, is, I hope I haven't led you astray by introducing this additional algorithm from over 2 millennia ago and saying that it's a good algorithm. So let me prove to you, hopefully, that it is a good algorithm, meaning that it's fast. And that brings us to the question of, how is it that we can determine how fast an algorithm is? Which means we're going to need some code in Go to time functions. And so let's show what that code is. So we're going to need a couple more packages here. We're going to need a time package and a log package. And VS Code has actually grayed those out a little bit because I haven't used them. So I want to use them. And what I'm going to do is I'm going to declare two integer variables and set them equal to values that are on the order of, say, 1,000,000. I'm going to make them have 7 digits in them. So I'm going to say x is colon equal to, and I've got two numbers here, but punch in your favorite numbers. It's not really going to matter. 3782026 for x, and y equal to 2731479. It would be cooler if I could generate two random integers here within a specified range, and we're going to know how to do that in a later chapter. We just don't know how to do it yet. So I'm going to say hold on to that for now. I'm just going to plug in these two arbitrary numbers off the top of my head. Now, we're going to think about this process as a stopwatch. So I want to click go on the stopwatch. The first thing I'm going to do is time trivial GCD. And to do that, I'm going to go in and declare a start variable that is equal to time.now. So Go is keeping track of the time on your computer behind the scenes, and time.now is going to give us a time object. We'll talk a lot more about objects later on in the course. We don't need to go deep into this for now. I'm just going to show you some code that you can use to time any function that you like. So I'm going to start the stopwatch. Think of this as start the stopwatch. And then I'm going to call trivial GCD of my two integers. I'm not going to set them that equal to each other, or set that equal to some variable. I'm not going to say like m colon equal trivial GCD, because I'm not going to use m, and I just want to run the function. I don't care about the value so much, so I'm just keeping this just to the function call itself. And then I want to say, once the function is complete, I want to click the stop button on the stopwatch. And the way that we're going to do that is to use time.sense, which comes from this time package. And it's going to take a time variable. And the time variable we want to give it is start. So it will subtract the difference of the time between when time.now got called and when time.sense of start gets called. So this stops the stopwatch. So the only thing between the start and the stop is the call to the function. It would be really bad if I had a bunch more code that was present in between start and elapsed. So I just want the function call in there. Keep that in mind. And then I want to print whatever the value is in elapsed in a nice form. And the way that I'm going to do this is I'm going to call log.printf, and I'm going to say trivial GCD took, and we're going to be formatting what winds up being a time object, which is represented behind the scenes as like a float. I'm not going to talk so much about formatting right now, but I'm just going to say if we want to represent this in a nice way, I'm going to call log.printf, and when I say %s, it's going to take the variable elapsed and it's going to print it out in our logs in a nice way. So if I were to print the variable elapsed, we're going to see a messy variable because it's an object that has different attributes. And instead, this is going to print it in a nice fashion. This is code to just have handy, okay? Where we have start equal time.now, stop the stopwatch, and then print to console in a pretty way. All right. So when I save that, let's compile and run and see what happens. And it tells us trivial GCD took, and then it prints the time. And the time that it takes is 1.157 milliseconds. So those are thousandths of a second. So it completes in like 1,000th of a second, which is pretty good, okay? So let me do the same thing for timing the Euclid approach. And here I'm going to introduce two more start and elapsed variables. So we're going to need a start2 equal to time.now. Again, that starts the stopwatch again. And then I'm going to call the function that I'm interested in. Note, I'm calling Euclid GCD on the same two integers. I wouldn't want to call it on two different integers. I want to make this a fair comparison. And then I'm going to have elapsed2 equal to time.sense of start2. So we hit stop, and then we print it. Log.printf and say Euclid GCD took %s colon or comma elapsed 2 and print that message to the console. So we can save that and go build and run GCD. So here trivial GCD was a little bit faster. It was less than 1 millisecond, and now it's into 864 microseconds or millionths of a second. That's actually that's nearly when we round up. That's going to be 1,000th of a second. Meanwhile, Euclid GCD took 709 nanoseconds. Now, a nanosecond here is a billionth of a second. So Euclid GCD is quite a bit faster. It's about a little more than 1,000 times faster. If we take the ratio of those two times, then we would see that Euclid GCD is a little over 1,000 times faster on these two particular inputs. And one of the things that you might be worried about at this point in time is you're thinking, why in the world did I make you implement these algorithms just to see one algorithm that finishes in 700 billionths of a second and another one that finishes in about 1,000th of a second? Like, what's the big deal? And the way that I'm going to answer that question is to say, okay, great. Each of these algorithms is pretty fast when we have 7-digit numbers. So pick your favorite two numbers, 2 digits, and add 1 digit to each of those, x and y. And then I want you to save it. And let's compile and run it again. So in this case, the trivial GCD takes about 10 times longer. Before it was taking like 1 millisecond, now it's taking 10 milliseconds. Whereas Euclid GCD, strangely, and this is because of it's proceeding so quickly that it's just fast, and they're going to get a little bit of noise here. It took even less time on these larger inputs. So we had two numbers that were 10 times as large, or multiplied by approximately a factor of 10, had an extra digit. Trivial GCD took about 10 times slower. Euclid GCD, still about the same, lightning fast. Still in under a microsecond, under a millionth of a second. That's pretty fast. And then if you don't believe me still, let's add another of your favorite digits to the end of x and y, so that now we have 9-digit numbers. So these are on the order of 100 million. And we're going to say compile, and let's run again. And now we see Euclid GCD is still just as fast, but on my machine, the trivial GCD is taking now 87 milliseconds. And if we want to go one more digit, what's going to happen? We're going to compile and run. And now we have a wait. We're now up to 876 milliseconds for trivial GCD. So each time we're getting about 10 times slower. And my guess is your computer might be a little bit slower than mine, so you might even be starting to see somewhat of a wait. I'm going to, especially if you're running this on a laptop, just because I'm on a relatively new, at least at the time of this recording, desktop computer. But I'm going to take this to even one more digit and see what happens on my machine. And now I've got to wait. And all I'm doing is computing a GCD. And those numbers aren't, I mean, they're large numbers, but they're not inconceivably large. If you punched that into a calculator, you'd want to get an answer in faster than 10 seconds. And Euclid GCD has absolutely no issue with this. There's just a little bit of noise. It is still faster than a millionth of a second. And yet trivial GCD is now getting 10 times slower each time I add a digit. So that's it's a simple type of illustration of this, because we have short algorithms. But what we're getting at is a much deeper principle in data science, which is that you might think that coming to programming, we have fast computers. So what's the point of having fast algorithms that are very fast, especially for these sort of simple tasks? Aren't computers just fast? And the counter to that is that, yes, but we also live in an era in which the data are getting larger and larger and larger. We're drowning in this enormous sea of data. And so when the data get larger, then having efficient algorithms becomes even more important, because when you have one algorithm that's an improvement on another algorithm, often what you see is this type of behavior. The larger the data, the larger the ratio between the runtimes of your previous approach and your new improved approach. So it's actually the opposite of what you might think is true, which is that having fast algorithms is more important than it has ever been. It's still just as relevant, if not more so, than it has ever been. And we're getting at that from the perspective of computing a greatest common divisor, which means that this is going to be, that's, as I said, a relatively simple type of question that you would ask. So these sorts of things that we're seeing here is a larger paradigm that we're going to see regardless of whether we're computing a GCD or doing something much more sophisticated like charting the movements of stars, just to take a random example. That might not actually be so random. The question is, we've seen that Euclid's approach is really good and it's worth discussing and worth knowing about. We have another approach, which is the sieve of Eratosthenes, and we want to say, well, that's our other beautiful algorithm from the ancient Greeks. Is it going to do really well also? And to answer that question, we're going to need to learn a little bit more about arrays and how they're implemented in Go and the quirks that Go can have associated with arrays. So that's what we're going to need to talk about next. But in the meantime, I hope you enjoyed this. I certainly had a great time. And I hope I'll see you next time. Until then, happy coding.